Hi, I'm Joe, and welcome to another update of my household robot build. I've been working on this thing for about a year now, and wanted to create an overview of how it's gone. It turns out that this project has been less progress and more just identifying all of the problems, the reasons why we don't have these things yet today. The initial idea for this robot was very simple. I wanted to make something to help the elderly or the physically disabled. I had a back injury once, and it makes you feel really helpless when you have a hard time picking something up off the floor because you got to bend over to do it. So I embarked on this project with the idea that I would make a robot that could pick up things, do maybe some basic cleanup, and remember where it saw things. Like I can't remember where I put my glasses, so the robot would be able to say, well, I saw them over here, and maybe fetch them for you. That would be pretty cool. At that time, the task seemed like it should be simple. Machine vision is quite good. Also, we have LLMs to help interpret natural language, so the robot will know what you're talking about. And all the mechanical stuff seems like it's been here forever. All of my life anyway. Servos, motors, stuff like that. How hard can it be? Famous last words. But I jumped right in, acquiring some parts. It looked like hoverboard motors would do the trick for driving it around. A 2D LiDAR would help with navigation. A simple board camera, and the Jetson Orin Nano, which is now the Jetson Orin Nano Super, for doing the machine vision and maybe some language processing. That, of course, didn't help with trying to manipulate any objects, but I figured, I'll get to that later. One of the things that I knew is this robot had to be tall enough to see over a countertop. So I built up a chassis out of plywood and MDF, and it ended up looking like a wooden traffic cone, but that was fine. I could start experimenting with these things. I started with just simply being able to move around without hitting things. Now, the 2D LiDAR, though a fairly affordable option, turned out to be problematic here because, well, it only sees in 2 dimensions. That's okay for a robot vacuum or something that's flat, but for this thing that stands up tall, where do you put the LiDAR? If you put it up high, it may trip over something low, and if you put it down low, it could clothesline itself on the edge of a table. So I tried putting it up high and at a downward angle to scan the ground in front of it as it rolled forward. But when you're driving around, rolling forward isn't the only thing you do. Say if the robot is close to an object and turns, the LiDAR may fire right over the top of it, and then it'll hit the object when it tries to go forward. And as I did these tests, I also discovered that the hoverboard motors were not a good choice. They are good at going fast, but not really very good at moving slowly and precisely. A big problem was that it would take very little energy to make the robot move at all, and then once it was moving forward, if it hit anything, a tiny little edge, even a piece of string laying on the ground, it would possibly stop the wheel. And it would throw the robot way off course if it hit on one wheel and not the other. So at this point I began a very long fight with motors and controllers. At first I thought, well, if I had a motor controller that would respond more quickly, I could maintain RPM. And so I ended up building my own homebrew motor controllers that were instantaneous in their response. These worked great, but still didn't get past the problem. I tried to compensate for this using machine learning. Yes, it's way overcomplicated for making a motor turn, but hey, I like machine learning, so I figured I'd give it a try, and I fought with that forever. I got some improvements in the results, but it still did not fix the problem. And so I finally caved in and moved over to some worm drive DC motors. These don't turn very fast, but they have a lot of torque, and they're not very affected by small bumps in the ground. And with these motors, and the help of a little machine vision tutorial, I was able to put something together that would track my face, and the robot would move around and keep a certain distance from me. That felt so good. I needed that success. But I still had a long ways to go, and other problems to solve. The glaring one was still the LiDAR, and how I perceive the environment. I looked into all sorts of things, stereo vision, and 3D LiDARs, but they were all quite expensive. But I found a nice solution in a time-of-flight camera. Time-of-flight camera is kind of like a solid-state version of a 3D LiDAR. It basically acts as a camera, only the pixels, instead of returning color values, are returning distances at every point in the image. This was fantastic, and I jumped right into trying to use that. The camera didn't work properly with the Jetson Orin Nano, so I acquired a Raspberry Pi 4 to do that processing. The Raspberry Pi 4 is a system that the camera was really designed for, and this worked out fine. But I was also working in Python, which turned out to be too slow to process these pixels one by one. I couldn't find any libraries in Python that would do what I was asking them to. So I had to move over to C and then of course C++ because the C libraries didn't work either. But with that in place, I was beginning to get some success. So I had to build a head for the robot to hold the time-of-flight camera and the vision camera. Now I had a platform that could move around and I could start really experimenting with this navigation stuff. But I really needed some more data. I needed odometry, so that the robot would know how far it moved. This would move the point cloud around in its perception of the world to make sure it knew where it was. My original plan was to use the encoders from the hoverboard motors, but now that I've gotten rid of the hoverboard motors, I needed a new solution. I experimented with the AS5600 magnetic potentiometer as basically an absolute position sensor, and I was very pleased with the result. So I was able to use that, putting a magnet on the end of the motor shaft and placing the sensor on the outboard side of the wheel. And now I had very good odometry. With that combination, I was able to start writing some programs to make it actually drive around randomly and make sure it wouldn't hit stuff. And you know what? It hit stuff. Things were not working right at all. Well, that was a combination of some slow programming in Python, buffer issues, and IMU drift. I was able to compensate for these problems by using a combination of odometry and IMU data to try to figure out which direction the robot was pointing. And the drift was pretty small at that point, but it was still there. And as I was building some band-aids for the navigation just to get it going, I was starting to have problems with the robot tipping over. And at one point, it fell over completely and broke its neck and head and face. Fortunately, it didn't damage any of the hardware inside of the head. But I decided that this robot now needed some reflexes to react to things happening to make sure it wouldn't tip itself over. It wasn't foolproof, but it helped dramatically, and also made the robot start to feel a bit more alive. It was responding more to things that were happening around it. And with those in place, I began to experiment with machine vision again. And of course, now that I had a head that could pan and tilt, it seemed good to make it so that it would track my face. At this point, it became very clear some of the problems with using servos for the neck. Since the hobby servos I was using didn't have any positional feedback, the robot wouldn't know which direction the servos were pointing while it was transitioning from one point to another. This caused problems for my navigational band-aids, where it would use combination of the IMU data as well as odometry data to know which direction the robot was pointing. The servo's transition period would completely throw that off. And so now I had to do my face tracking too slowly, and the robot would overshoot often as it moved its head to try to find the new position of my face, which was now adding to the pile of strikes against this particular robot build. And I knew from the beginning this one wouldn't be very useful. It had no way to manipulate its surroundings. It was time for a ground-up redesign of the robot. And of course I had to first address the issue of, well, what is it shaped like? What's the form factor? How is it going to manipulate its surroundings? For this, I did a lot of brainstorming with my brother, and we came up with this idea of a gandroid, sort of a goose-shaped robot. You got the big chassis on the bottom, and an arm that comes up with the head on the end of it, and also an end effector, a gripper of some sort, to manipulate its surroundings. It definitely seemed like the minimalist way to go about this. Reducing the number of mechanical parts is about the best thing you can do in almost any situation for making a good machine. With that decided, I needed to address stability from a mechanical standpoint first, before I even got into reflexes. The way to do this was to make a chassis with 4 wheels instead of 3. This would be much more stable. But when you're talking about a 4-wheel chassis, it needs to have some way to flex in order to keep all 4 wheels on the ground at once when the ground is uneven. Because let's face it, In most situations, the ground is uneven. I have an old house, the floor is not quite flat, and there are door sills between the rooms. These are bumps that the robot must get over, not to mention rugs and, well, other things that might be lying on the floor. So I came up with a fairly unique suspension design, and it turned out to perform very, very well, way beyond what I was expecting. I also was remembering my trouble with the robot falling over and wanted another way to give it a sense of if it's leaning or something like that. And so I built in some load cells that would measure the force on the robot if it was tipping forward, backward, left, right, something like that. This will also be useful when the robot is picking up an object. It will allow it to know if it needs to move the head, neck, arm gripper thing backward or forward or whatever in order to make sure the robot doesn't fall over. As I worked my way upward, I needed to make this arm piece. Now, a robot arm in itself is quite a design challenge. I needed a lot of strength for this arm. It's fairly long and I needed a useful payload. I decided to try using worm gear motors again. I very much liked them as drive motors. Let's find out how they work for actuators. And I began to experiment using those same magnetic potentiometer chips in order to find the position of the servo. This took some experimentation, but actually turned out to be fairly easy to do. Armed with this, I got back into my 3D CAD modeling, which is not my strongest skill, but I went at it and created an arm. And that's where my last video ended. From there I built a rather primitive upper section to the arm, and then I had to create a head. Now the head has been changed. I've taken the computing hardware out of it. I want to make it lighter weight. Since it's now on the end of an arm, the weight of the head takes away from the payload the arm can lift. So I reduced it to being just a camera and the time of flight camera with its own little computing module on the back. Now that's something I've worked on behind the scenes a bit, and I keep on teasing it and mentioning it. Really what I've done is I've paired the time of flight camera with a Raspberry Pi Zero into a very small module and a new IMU, the B&O 055 by Adafruit. This particular IMU has a magnetometer built into it. Not only does it measure gravity and rotation, but also looks for magnetic north. This will help with navigation quite a bit, at least I hope. It seems to be fairly accurate with pretty low drift. I combined these three elements on a single board, and then I've created software in that board that takes the time of flight camera data and turns it into a voxel image. Now this is something new that I've been tinkering with for a long time. With robot navigation, I've seen a lot of ways of doing it, but none of them seemed like the perfect answer. And then I started to think about two-dimensional images. We have cameras that take a picture of the outdoors. When the camera takes the picture, it's not turning the outdoors into a bunch of vectors and things like that. What it's doing is it's recording the color of each pixel. A voxel is a three-dimensional pixel. Think of a Minecraft world. Every block is a voxel. So now I'm using the 3D time of flight camera to create a voxel image of the world around it, using each voxel as a point in space. And in this case, it's got a resolution of 1 decimeter, 1/10 of a meter. I think that resolution will work, and it also is reasonable in a memory capacity. Using voxels for the robot's sense of its surroundings is a very memory-heavy way of doing things, but the processing end of it is actually pretty light, because you're simply storing everything in a 3D array. Also with this, these voxels can be tagged with all sorts of information. Every voxel could be given a color, possibly a material, whether or not it's washable, or if it's a curtain that could be pushed aside, or if this voxel is a door that can be opened. By using voxels, we can tag every little cube of space in the environment the robot moves around in. Now this is just theory right now, at least on my part, so stick around to see how it works out. And that's where we are now. The few steps I have left to do on this chassis is to wire up the position sensors for the arm, get all the servo loops working properly, and then make it interface with a higher level computer, in this case my Jetson Or Nano Super, to begin trying to make this robot more useful. And of course I will still have to develop a gripper of some sort for the end. This is going to be an interesting challenge of its own. Robot grippers and hands are a significant portion of the engineering in any robot, mechanically speaking anyway. And again, that's not my strongest set of skills, so we'll see how it goes. So hold on tight, we're about to get the exciting stuff again. I'll be getting back to a lot of programming code, which I find is hard to make exciting in a video, but the results are exciting when you see it drive. So until next time, I'm Joe. Do the like and subscribe thing if you want. Signing off.
You kicked me. Sir, you are